Hello everyone, my name is Birthe and in this talk I will show you a functional account of probabilistic programming with possible worlds. In this talk we will put on our functional programming glasses to have a look on the possible world semantics that are used in logic programming to model probabilistic processes. We will look at turn monads to represent logical queries and a recursion scheme to interpret them. We will also have a look at algebraic structures such as boolean algebras and commutative semirings for interpreting such queries, and we will also have a look at some popular normalisation techniques. There is quite some research that crosses the boundaries between functional programming and logic programming. And although many programming aspects are of common interest, both paradigms have a somewhat different approach. Logic programming, for instance, focuses on models, or the being of things and what they are or what they represent. These are mainly non-operational aspects, such as well-founded semantics or stable model semantics. Functional programming, on the other hand, focuses mostly on processes or the doing of things and how they are done. So it's mostly operational semantics. And common processes in functional programming that model logic programming aspects are backtracking search, least fixed points of non-deterministic computations, or unification algorithms. But there's another big part of the spectrum that is less explored, which is probabilistic programming that takes into account the non-deterministic or probabilistic nature of some programs. For example, in logic programming, you have the so-called possible world semantics, in which every possible situation is modeled together with a probability. And in this work, we will have a functional view on the concept of possible worlds so that we can combine the probabilistic programming approach with the functional programming paradigm. Let's first have a look at some background about possible worlds. And for this, we will have a look at an example. Consider a small gambling game where we have to toss a coin and draw two balls, choosing from red balls and blue balls. Each of these actions has a probability of success. For instance, the probability you toss heads is 30% and consequently the probability of tails is 60%. Similarly, the probability of the first drawn ball being red is 30%, or for blue it's then 70%, and for the second ball it's 20% or 80% for blue ball. You win the gambling game if you toss heads and you draw a red ball, or if you draw two balls of the same color. And we are wondering what the probability is to win this game, given the probability of the separate actions, as we have here. And also how we can compute this probability, of course. A way to do this, and actually the way we will look at in this presentation, is by computing the so-called possible worlds. That is, we model every possible situation of our gambling game, together with its probability. For example, you can imagine the situation or the world in which we toss tails and draw two blue balls. The probability of this world can be computed by using the individual probabilities of the actions. Similarly, we can do this for all possible worlds, which are 8 situations or 8 possible worlds in this example. Then, in a next step, we can verify for which of our worlds our win query is true. So, there are those worlds where we toss heads and have a red ball, or where we have two balls of the same color. And we add up the probabilities of these worlds to get the total probability of winning the game, which is in this case equal to 77.2%. Alright, now let's see how we can look at this concept through our functional programming classes. We can represent the individual actions by facts, where H represents tossing heads, R1 is drawing a red ball from the first stack, and R2 is drawing a red ball from the second group. And a possible world is then a collection or a set of facts. We represent a query by means of the well-known non-determinism monad, which indicates the non-deterministic character of logic programming. This query data type is monadic, and its monadic structure actually aligns very well with the conjunctive structure of the queries. And indeed, we can represent true by means of a return, and we can represent conjunction by means of monadic sequencing. On the other hand, it also has an alternative instance. An alternative is a monoid on applicative functors, and this alternative instance of queries aligns very well with their disjunctive structure of the queries. And indeed, as you can see, we can represent false by means of the alternative's empty, and disjunction by means of the alternative binary operator. In a next step, we can capture query literals in a lit constructor. So we add now literals to our query data type. Literals range over facts, f, so we add f to the data type as well, to distinguish now between values a and facts f. Literals themselves consist of a fact lit f that indicates its positive or negative occurrence, and of another query. And as binding, monadic binding aligned with conjunction, literals contain an extra query so that, for example, red1 means the conjunction of the positive occurrence of R1, so drawing a red ball from the first stack, and the query true. So trivially, we fill in true for this extra query. For example, we can now write the query for winning our gambling game as follows by means of the query, the facts, and the worlds. So now we have defined a syntax for queries in terms of a term monad. So let's see how we can give semantics or meaning to these queries, or how we can interpret them. As is common for algebraic effects, we require handlers to ensure that the interpretation of queries respect the laws we expect them to. We do this by providing a structural recursion scheme which takes two generators. One for interpreting values, so interpreting a value A into B, and another one for interpreting facts, so we have a function of f to b. And with that in place, we can interpret entire queries as well. And we do this in terms of a boolean algebra B. Let's have a better look at this boolean algebra. A boolean algebra is an algebraic structure that provides a framework for interpreting logical formulas. It has 5 components: a bottom, a top, negation, conjunction, and disjunction. And furthermore, this structure should also adhere to several laws, as you can see here. So we have idempotence, commutativity, associativity, absorption, distributivity, universal bound, and complementation. Some obvious instances of these Boolean algebras are, for example, Booleans themselves. And with these Booleans, we can decide on the truth of a formula given the truth of the facts. So as you can see here, the operations of Boolean algebra align very well with the Booleans themselves. Another instance of Boolean algebras is the function type. And it does form a Boolean algebra if the result type B is also a Boolean algebra. And the implementations of this instance are mostly pointwise for their components. And with this, we can write a models function that indicates whether a query is true in a given world. So given a query Q and a world F, we can decide whether this query is true or not. Third, the subsets of a set also form a Boolean algebra. And this is particularly interesting when the set contains or consists of facts and thus represents a world. For this implementation, we use the functions from Haskell's data.set library with their meanings as indicated in that library. With this instance, we can, in a naive way, compute the possible worlds of a query. So given a query, we compute a set of worlds. But what we desire is to interpret a query in terms of a probability. And the probability is a floating point number between 0 and 1. But unfortunately, probability distributions do not form a Boolean algebra. And I'll show you why. First of all, conjunctions generally do not align with multiplication. The probability of the second query of the multiplication contains a dependence on the first query, as you can see here. And second, also disjunction does not align with addition, because there is a probability that should be subtracted to compensate for the overlap between the two queries, as you can see here. And there's even more, because the idempotence, universal bounds, absorption laws, and so on of Boolean algebras, they are not satisfied. So how can we make it possible to interpret queries using a probability distribution? The solution lies in normal forms. If we have two queries, Q1 and Q2, that are equivalent according to the Boolean algebra laws, we can normalize both queries so that they remain equivalent under different laws. And in this normal form, we can then interpret them using a probability. And this probability interpretation should be the same for both queries Q1 and Q2. Now, it is key to choose the correct normal form and the correct associated algebraic structure for which the normal forms are equivalent. Following Darwich, we choose for the so-called d-DNNF, or deterministic decomposable negation normal form. And this normal form makes queries deterministic, which means that every two subqueries that form a disjunction are mutually exclusive, or no world makes both queries true. Similarly, it makes queries decomposable, meaning that every two subqueries that form a conjunction are independent, like this. Furthermore, we only feature negations directly on facts. And actually, we are lucky, because we don't have to look far for such a d-DNNF, as our possible world representation is isomorphic in fact to this structure. And indeed, it is a disjunction of mutually exclusive worlds, and each possible world is a conjunction of independent facts. And indeed, also negations do only appear on facts. So if we normalize our queries into this deterministic decomposable negation normal form, they are equivalent under the remaining laws. And these remaining laws form another algebraic structure, which we call the commutative semiring. The queries in normal form can then be interpreted in terms of their probability. So let's have a more detailed look at this other algebraic structure, the commutative semiring. A commutative semiring features four operations: a 0 with addition and a 1 with multiplication. Also, these semirings come with several laws, and in comparison with regular semirings, commutative semirings also feature a commutative multiplication, the first law here. And hooray, probabilities indeed form a commutative semiring. The main advantage of the deterministic decomposable negation normal form is that we can now interpret queries in terms of commutative semirings in linear time. But there are some other popular or famous semirings that are of common interest, and one of them are, for instance, the dual numbers, with applications in physics, robotics, but mainly also in automatic differentiation techniques, where a dual number represents a number, the first component, together with its derivative in the second component. So in this instance here, you can see in the first component that we map 0 to 0, 1 to 1, plus to plus, and times to times. And in the second component, you can see that we have computed the derivative with, in the multiplication case, the derivative law that you have learned in high school, probably. The semiring can be used, for instance, to perform gradient descent of the probabilities of the facts based on the probability of the entire query. And another commutative semiring instance is the so-called tropical max or tropical min semiring, which is an example of a commutative semiring without an additive inverse. It selects the maximum for addition or for disjunction, and it adds up for multiplication or for conjunction. For instance, with this semiring, we could find the highest cost if positive facts would be labeled with a cost. So we have now introduced one way of interpreting queries via a deterministic, decomposable negation normal form, namely the possible world semantics. But this approach is not very time efficient, and we believe we can do better. And indeed, interpreting a query via the possible worlds has an exponential time complexity. But fortunately, the possible worlds is not the only d-DNNF. Indeed, several compilers exist that use heuristics to more efficiently compute more compact d-DNNFs for a query, with C to D, D sharp, and D4 the most common ones, where they each build on each other, and D4 is the most recent and also the most efficient one. But all of these compilers require the query to first be in CNF or conjunctive normal form. So we have implemented the approach with D4. For example, the query win for winning our gambling game can be transformed into a more compact equivalent that is in deterministic, decomposable negation normal form. And for this we use the D4 compiler. This is what it looks like. For more details about the implementation, go have a look at the paper and in particular at the code repository. So with this more efficient path below, we first transform the query into its normal form and then interpret it as a commutative semiring, which is most frequently in terms of its probability. But can we compare between Boolean algebras and commutative semirings? Because both come with their advantages and disadvantages. So although the interpretation of a query in terms of commutative semirings is more expressive, because we can do probability distributions, and also more efficient, because we can use the named heuristics, such as D4, it also requires an additional normalization step, which forces us to use a trivial implementation for interpreting variables. And at the base of this problem is the non-compositional nature of this normalization. And indeed, we consider positive variable occurrences to map to true or to 1, and negative occurrences to false or to 0. And indeed, with the commutative semiring implementation, our queries will always have the form QF unit. With a Boolean algebras, we can differentiate between facts and values. So we have a query in the form QFA, where F represents facts and A represents our values. But on the other hand, time complexity in terms of Boolean algebras is exponential, so not so nice. In the paper and the code, we elaborate more on this topic. For example, we show how a least fixed point operator enables also cyclic models, such as graphs, networks, or the famous social smokers problem. And we do this with the same possible world semantics approach. So go check out the paper if you are curious how this works. Also, in the code, we unravel the implementation with the heuristics for transforming a query first into conjunctive normal form and then with a compiler, which is here D4, into decomposable, deterministic, negation normal form, and then into commutative semirings. We also give some more code examples, so go have a look at the repository if you're interested in the more practical implementation of these ideas. So, in summary, in this work and with this talk, we have presented how we can take a functional view of probabilistic logic programming in terms of possible worlds. We've put on our functional glasses and viewed this alternative flavor of probabilistic programming in terms of typical functional programming concepts. In particular, we have represented queries using a term monad, distinguishing between facts and values. Then we have used a structural recursion scheme in order to interpret these queries in terms of boolean algebras, with the possible world semantics as an instance that was of particular interest. However, we wanted to be able to interpret the queries using a probability distribution, but these probabilities did not form a boolean algebra. So we have used efficient normalisation techniques such as D4 to transform the queries into a deterministic, decomposable negation normal form and interpret them by means of a commutative semiring. So thank you for your attention, and I'm happy to answer any of your questions.